Let's look now at section 8.3. Let's talk about trigonometric integrals. In this section, we're going to be looking at how to integrate expressions that involve sine, cosine, tangent, and so forth. So we're going to handle this in cases. There's going to be different cases, different versions of integrands which contain trigonometric functions. Depending on which case you have, you'll have one different way of integrating. The nice thing about having cases is that as long as you recognize what case you're in, you pretty much know what to do. It's not quite a formula, but it does give you a very straightforward, methodic way of integrating. There's not a lot of guesswork once you know what case you're in. The problem can be sometimes, well, there's a lot of cases, and it may be a little difficult to remember which one we have. So in any event, let's take a look. Let's begin with integrals that involve sine and or cosine. So integrals involving sine of x and or cosine of x. Okay. When you have sine of x and or cosine of x, the possibilities are you might have something like this. You'll have sine of 2k plus 1 of x, cosine to the power n of x dx. You say, what does that mean? 2k plus 1 is a generic way of saying an odd number. Because after all, if you multiply something times 2, it's even, and then add 1 makes it odd. So here, the first case is what happens when you have sine to an odd power. Notice cosine, we just say cosine to the power of n, so we're not really saying it's even or odd, we're just saying, hey, we have cosine to some power. Incidentally, that power might even be the power 0, so it's possible that we don't even have that at all. But here, the thing that matters is that 2k plus 1 should be an odd power. Okay? If that's the case, what you're going to do is you're going to strip off a single power of the sine of x. Or in other words, you're going to write this as the integral of the sine of 2k. If this was a power 19, you would say, okay, that's power 18. And now you're going to take that single sine of x that was left over as a factor, and you're going to separate that. Here, I'm going to write the cosine to the power n first, and then I'll have sine of x dx. Okay, so why would we do that? Well, let's take a look at an example to see why that should happen. Let's say we have the integral of sine to the third power of x, and here we'll say cosine to the sixth power of x dx. In this case, we have an odd power of sine. Here, this could be even or odd. It doesn't really matter. All that matters for this case is sine of x has an odd power. Okay? When you have something like this, you're going to rewrite this as, okay, take sine of 2x, oh, sorry, not sine of 2x, sine squared of x, cosine to the sixth of x, and now you notice that cosine squared of x, you're still missing one factor of sine of x. Okay, so write that one here at the end. Okay, so now what? All right, well, first of all, notice that we have this. We have an even power here. Here, this just retained its power from the original problem. And here you have a single copy of sine of x dx. What you want to do now is you want to use the Pythagorean identity on this portion. Why do we use the Pythagorean identity? Because the Pythagorean identity allows you to switch the square of a sine into the square of a cosine, or vice versa. Here, we can write this as the integral of, instead of sine squared of x, we can write 1 minus cosine squared of x. That's cosine to the sixth power remains the same, cosine to the sixth of x, sine of x dx. You say, okay, sure, that equals that, but now what? Notice now that all of this is in terms of cosines. cosine to the second power, cosine to the sixth power. If you distribute, that's cosine to the eighth power. Everything's in terms of cosine, well, except that one. Well, yeah, but that is the derivative of cosine of x. Well, if you include a negative there. Yeah, but negatives are like saying a constant -1. Those are easy to come by. So except for maybe a constant, this is the derivative of expressions over here. Or in other words, we can take sine of x dx and treat it as a differential. So here, this will be treated as your differential. Which means we can use a substitution. Here we're going to take cosine of x and write that as u. Cosine of x is equal to u, which means du is equal to negative the sine of x dx. We have almost exactly that. Let's just multiply both sides by -1. So -1 du is equal to sine of x dx. And so now this can be written using a substitution. Integral of 1 minus, instead of saying cosine squared of x, we just say u squared. Cosine to the sixth of x, we can just say u to the sixth. And here sine of x dx is -1 du. We can go ahead and distribute that out, make things nice. Here, that's going to be -1 times u to the sixth times 1. Oh, that's negative u to the sixth. Here, -1 times u to the sixth is negative u to the sixth times negative u squared, that's positive u to the eighth. Here, just distribute u to the sixth and then change the signs of everything. But now that just uses the power rule. This can now be written as u to the 9th over 9 minus u to the 7th over 7 plus some constant of integration. And finally, since u is just the cosine of x, we can now back substitute to give ourselves a result of cosine of x to the power 9 over 9 minus cosine to the power 7 of x over 7 plus some constant of integration. And that makes us happy. Note that if we change the roles of these two functions, we're still going to do the same thing. If instead of having an odd power on the sine function, we have an odd power on the cosine function, it's going to work very much the same way. So here, let's say I have, instead of sine to the third of x, cosine to the sixth of x, let's say I have sine to the fourth of x, let's say cosine to the fifth of x dx. Same idea, except now, instead of this one having an odd power, well, now this one has an odd power. Okay, same thing. Take the one that has the odd power, strip off a single one, and use that along with dx to form the differential for a substitution. So the way it looks in this case, we're going to take the integral of sine to the fourth of x. Okay, that one has the odd power, so we're going to strip off a single one. So we're going to write that as cosine to the fourth of x times the cosine of x dx. This right here will be your differential. So that means that cosine of x dx is your differential, which means that the rest of the function needs to be in terms of things whose derivative is the cosine of x. Or in other words, the rest of it needs to be in terms of sine of x. Okay, well that's already in terms of sine of x, but that's not. Well, yeah, but Pythagorean identity allows me to change sines for cosines and, in this case, vice versa, cosine to sine. Here I'm going to write this as the integral of sine to the fourth of x. The Pythagorean identity only works on the squares of sines and cosines, but since this is even, you can always write this as a square to a power. In this case, cosine squared of x, quantity squared. If you square a square, you get a fourth power. But now the Pythagorean identity works right in there. We can write this as the integral of sine to the fourth of x times, instead of cosine squared of x, we'll write 1 minus sine squared of x, quantity squared, cosine of x dx. And now, all of this stuff is in terms of sines of x, or constants. This is the derivative of the sine of x, which means this whole thing will be the differential. And so we can substitute now. So let's go and use the substitution. Let's take the sine of x to be our substitution u, which means du is going to be cosine of x dx, which here we don't need to change anything. That's exactly what we have. So this will now become a much simpler integral, in fact, the polynomial integral. That's going to be, instead of sine to the fourth of x, that's just u to the fourth of x. Or actually, just u to the fourth, not even of x, right? U to the fourth. Times 1 minus u squared squared. Here, cosine of x dx is your differential du. That is now much simpler, but of course we should probably expand this so that it looks more, a little more friendly. We can write that as u to the fourth. 1 minus u squared, the quantity squared, is going to be 1 minus 2u squared plus u to the fourth du. And then distributing u to the fourth is going to give us the integral of u to the fourth minus 2u to the sixth plus u to the eighth du. And now that's about as simple of an integral as one can hope for. We've gone from powers of trigonometric functions to a polynomial. And polynomials are reasonably nice to handle. Here the integral of u to the fourth minus 2u to the sixth plus u to the eighth with respect to u. We're going to end up with u to the fifth over 5 minus 2u to the seventh over 7 plus u to the ninth over 9 plus a constant of integration. And of course, u is a stand-in for the sine of x. So for our final result, let's substitute that back in. And so our result is sine to the fifth of x over 5 minus 2 sine to the seventh of x over 7 plus sine to the ninth of x over 9 plus some constant of integration for that nice minty smell. And there's our result. Now, you might say, okay, if sine has an odd power, okay, I strip off 1 from sine. If cosine has an odd power, I can strip 1 off of cosine. Oh, what if they both have an odd power? Well, then you can choose. You can either choose to do it this way or choose to do it this way. Okay, so in the case that both of these have an odd power, just pick whichever one you want and work with that one. Strip off 1 from that one. So the real question is, what happens if neither one is odd? Well, that's our next example, and that's our next case. What happens when we have integrals of sine to the 2k of x cosine 2n of x dx? Here we use 2 different letters because, of course, here this might be 2 times 3 and this might be 2 times 1. These are both even powers, but no one ever said they're the same even power. Okay, so if you have an odd power on even one of them, you choose that power and strip off a single one. But what if they both have even powers? When you have an instance like this, what you want to do is you want to recall the following formulas from trigonometry. The power reduction formulas state that if you have the sine squared of x, that's equal to 1 minus the cosine of 2x over 2. Like this. And the cosine squared of x, something very, very similar. In fact, it's almost identical. The difference, instead of a minus, there's a plus here. So that's 1 plus the cosine of 2x over 2. These were derived from the double angle formula for cosine of 2x. Cosine of 2x is equal to 2 cosine squared of x minus 1. So if you solve for the cosine squared of x, you get this formula here. An equivalent version of the double angle formula for cosine of 2x is cosine of 2x is equal to 1 minus double sine squared of x. And if you solve for sine squared of x, you end up with this formula. So here, these are the power reduction formulas, and they really are just the double angle formulas reformulated a bit. The power reduction formulas. And these are to be used anytime you have both powers of sine and or cosine being even. If either of these are odd, you wouldn't do this. If either of these are odd, then you're using the previous case that we saw, right, where you take off the single odd power and use that as your differential. But if nothing has an odd power, if everything has an even power, then you'd use these. So, for example, we might have the integral of sine of x quantity squared dx. Note that we don't actually even have to have cosine of x, because here 0 is technically an even number, right? So here cosine to the 0 of x also qualifies for this case. And that's exactly what I have here. I have cosine to the 0 of x. Or in other words, I don't have cosine of x as a factor. So here I can say, okay, this does qualify in this category. It is one of these cases. So using the power reduction formula, I can rewrite this as the integral of 1 minus the cosine of 2x over 2 dx. That 2 is a constant. Everything here is being multiplied by a half. So let me factor that out. That's going to be 1/2 the integral of 1 minus the cosine of 2x dx. And now that integral is something I can do. Here, that's going to be 1/2 the integral of 1 with respect to x. Well, that's just x. Here, the integral of the cosine of something is the sine of something. So minus the sine of that 2x. But now, because here, this 2x, the derivative of this is 2, here I would need to divide this by 2 to compensate for the fact that there's something other than just x in here, basically just the chain rule, plus a constant of integration. Here I can distribute my 1/2, and this will give me 1/2 x minus 1/4 sine of 2x plus c. Here we could, of course, rewrite this a few different ways. Note that the sine of 2x can be rewritten using the double angle formula. So depending on what you're trying to do, in some cases you might actually want something in terms of just x. You might simplify that. But here there's no requirement other than finding the antiderivative, the general antiderivative. So for us, this is perfectly sufficient. In an application, you might actually need this in terms of x, so you would use trigonometry, but that integral is as is. The power reduction formula may need to be used repeatedly. So for example, let's say I have the integral of cosine to the 4th of x dx. Okay, so again, that's at an even power, and technically 0 is an even power, so that does qualify. So here, let me write this as the integral of cosine squared of x squared dx. After all, the power reduction formula works on the square of either sine or cosine. Here, that's a 4th power. We're going to write that as a square being squared. So now, by the power reduction formula, this cosine squared of x is 1 plus the cosine of 2x over 2. But now that whole thing is being squared. Okay. Now, if I square all this, that's going to give me the integral of 1 plus 2 cosine of 2x plus cosine squared of 2x. Here, I'm just going to head in 1 plus cosine of 2x times 1 plus cosine of 2x and distribute it. And my denominator, 2 times 2 is 4. 2 squared is 4. I can factor out that 4. So that's going to give me 4 times the integral of 1 plus the cosine, plus double the cosine of 2x plus the cosine squared of 2x dx. Notice, however, that we still have an even power of cosine here. Yes, I know how to integrate 1. Yes, I know how to integrate 2 cosine of 2x. I don't know how to do that. Oh, I have to use the power reduction formula again. So the power reduction formula, kind of like the integration by parts technique that we saw in the last section, may have to be used iteratively, meaning do it once, and if that's not enough, you might have to do it again, and again, and again, and again if necessary. So here, let's do that again. That's 4 integral of 1 plus 2 cosine of 2x plus, and now this expression here, I'm going to expand using the power reduction formula again. Okay, so here, cosine squared of x is equal to 1 plus cosine of double that x over 2. Okay, so 1 plus the cosine of double that x. Oh, but notice that x is already doubled. So what happens if something's already doubled and you double it again? Oh, well, now that's quadrupled over 2. Notice the power reduction formula, every time you reduce the power, you double the argument. This goes from 1x to 2x. So if you reduce the power again, this will go from 2x to 4x. If you did it again, that will go to 8x, and then 16, 32, and so forth. That won't change that denominator. It won't change that constant 1, but it will change the argument every time you reduce the power. Here, I can go ahead and give everything a common denominator. So here, let's write that as 4 integral of 2 plus 4 cosine of 2x plus 1 plus cosine of 4x all over 2. Those stayed the same. 1 plus cosine of 4x over 2. Here, instead of writing it as 1, I wrote that as 2 over 2. And instead of 2 cosine of 4x, I wrote 4 over 2 cosine of 2x. So now, they all have a common denominator, which means I can factor out that common denominator, and also, hey, look, those two combine together. So if I factor out the 1/2, that's 4 times a half, 4 over 2, that's 2. Integral of 1 plus 2 is 3 there. Hope I don't insult anyone's intelligence by adding 1 plus 2 for you. 1 plus 2 is 3, plus 4 cosine of 2x plus the cosine of 4x dx. And now, even though our arguments are in terms of 2x and 4x, we still just have cosine of arguments, which means that now we can integrate. All of these are accessible to us. That's going to be 2 times the integral of 3 with respect to x, that's 3x, plus 4. The integral of cosine of 2x is going to be the sine of 2x, but then we have to divide by 2 because of that expression here. The derivative of 2x is 2, which means you would divide by that 2. Plus, here, the antiderivative, the integral of the cosine of 4x would be the sine of 4x, but then the derivative of this is 4, so we would have 1/4 the sine of 4x, plus our constant of integration. Okay. So now, we can distribute and simplify, and we're done. 2 times 3x, that'll give us 6x. That's 2 times that 2 outside, that's 4. The sine of 2x. And then here I have 2 times 1/4. That's going to be 1/8. 1/2. The sine of 4x plus a constant of integration. All right, so let's see, is that... Oh, you know, I noticed I made a mistake here. This is over 4, but when I factored it out, I factored out the number 4. I should have factored out 1/4, since that's in the denominator. Thankfully, that doesn't change much until the very end. So that's not a 4 on the outside, that's a 1/4. So here, when I factor out this 1/2, 1/2 times 1/4 is 1/8. So here that integral remains the same, and that's 1/8. Yes, my apologies. That should not have been 4. That should be 1/4. So here, when we factor out the 1/2 from here, 1/4 times 1/2, that's 1/8. All of the stuff in here remains exactly the same, but now when we distribute, that answer will be slightly different. The coefficients are going to be changed here. So 3 times 1/8, that's going to be 3/8. That's still x, just the coefficient changes. Same thing here, that's the same, just the coefficient changes. So that's going to be 4/2, that's 2. So 1/8 of 2, that's 2/8. I can reduce that to 1/4. So 3/8 x plus 1/4 sine of 2x. And then here we have 1/8 times 1/4. That's 1/32 sine of 4x plus a constant of integration. Let's see, let me double check, make sure I didn't do any other mistake. I don't have any other mistakes. All right, that seems about right. Yeah. So that's going to be 3/8 x plus 1/4 sine of 2x plus 1/32 sine of 4x plus c. And that is our result. All right. So go ahead and give one of these a try. Find the integral of, let's say, sine to the 5th of x, cosine to the 3rd of x, dx. Okay. Go ahead and pause the video. Power 5, power 3. Go ahead and pause the video and work through it. And once you have a result, go ahead and unpause and we'll go through it together. Alright, so both of these have an odd power, which means I can choose whichever one I like and strip off a single factor. Here we saw in the previous examples that when we strip off a single sine, oops, that's the wrong one. When we strip off a single sine, we're going to have to worry about an extra negative that shows up because the derivative of the cosine of x is negative the sine of x. But when we strip off an extra cosine, there's no extra negative that needs to happen because the derivative of sine is just cosine. So here, given the choice, I'd rather take a single copy of cosine of x as my differential. It'll work for either one, but personally I think this one's a little nicer because I don't have to worry about that extra negative. So let's write that as sine to the 5th of x, cosine squared of x, cosine of x dx. This expression here can now be written using the Pythagorean identity as the integral of sine to the 5th of x times. Instead of cosine squared of x, we write 1 minus sine squared of x times cosine of x dx. But now, since everything here is in terms of sine of x, and cosine of x dx is the differential of the sine of x, we can say u is equal to the sine of x, du is the cosine of x dx, and so now our integral can be rewritten as the integral of u to the 5th times 1 minus u squared, and then cosine of x dx, that's your du. That can now be written as u to the 5th minus u to the 7th du. And now we've gone from a less than pleasant expression to something polynomial, which is a lot simpler to handle. The integral of u to the 5th with respect to u is going to be u to the 6 over 6 minus the integral of u to the 7th with respect to u, that's u to the 8th over 8 plus a constant of integration, as the prophecy foretold. So now we have u equals the sine of x, so substituting that back in gives us sine to the 6th of x over 6 minus sine to the 8th of x over 8 plus a constant of integration. Now when you tried it, some of you may have done exactly what I did, stripped off a single copy of the cosine of x. However, stripping off a single copy of the sine of x is also valid. And if you do that, you end up with a very similar expression, but not exactly the same. In fact, you'll get something like cosine to the 8th of x over 8 minus cosine to the 6th of x over 6 plus a constant of integration. So how could I get two different answers? Well, because remember, trigonometric equations are all related to each other. There is an identity that will transform this into something involving cosines. So here, if you took off a single copy of the sine of x and used that as your differential, that will still work. It'll give you something that looks very different from this, or at least marginally different from this. It won't look like this exactly, but it's equivalent. There is some way to transform that into this or this into whatever answer you may have gotten. So don't worry too much about the answer looking slightly differently, because that's to be expected, especially with problems that involve trigonometry. So now we've seen what happens when we have even powers of sine and cosine, odd powers of sine and cosine, and a mix of those. Okay, well that's it. There's nothing left. Well, sure, there's nothing left for sine and cosine, because for sine and cosine, the powers are either even, odd, or both, a mix of both. But what about the other trig functions? What about secant? What about tangent? So here, we're going to take a look at combinations of secant and tangent. You might say, what about cosecant and cotangent? The reason we're looking at these integrals in particular is because in the next section, we're going to use what's called trigonometric substitution, where essentially we're going to take something that's not trigonometric, and through some very strategic manipulation, we're going to end up with trigonometric expressions. Sine and cosine show up very often. Secant and tangent will also show up very often. Cosecant and cotangent will not show up anywhere near as often because of the choices that we're going to make in the next section. So in the event that you ever have something that involves cosecant and cotangent, generally the advice is, well, you can always turn those into reciprocals of tangent and reciprocals of sine, right? Or you can always turn everything into sine and cosine. So here we're going to see sine and cosine. We're going to see secant and tangent. The other two we're not going to see because at the very end we'll have a single example of, well, what if it doesn't fit one of these categories? And spoiler here, the answer is, if it doesn't fit one of these categories, just write everything in terms of sine and cosine, and then it will fit one of these categories. The reason we're going to look at secant and tangent on their own is because they show up often enough that we want to have a way of doing it that's a little bit faster than just rewriting everything with identities of sine and cosine. All right, so let's begin with, well, here, let's see. Integrals involving secant and tangent. All right, so the first example, or the first case rather, we're going to take something that looks like this. The integral of secant to the 2kx times tangent of x, or tangent to the power n of x dx. So here, we don't really care what the power of tangent is, just some power, right? Power 1, 2, 3, 4, 5, or even power 0, that's fine. What matters for this first case is that this one, secant, should have an even power. Okay? So, if you have an even power, what you're going to do is you're going to strip off a pair of these. You're going to write this as secant to the power 2k minus 2. You're going to take 2 off that power. You're going to leave tangent as it is. And now the 2 that you stripped off, that's secant squared of x, along with your dx, that'll form your differential. This is very similar to the technique that we saw for sine and cosine, except that for sine and cosine, you're looking for an odd power to strip off 1. Now you're looking for an even power and stripping off 2. Okay, so let's take a look at an example of how that works. Let's say we're integrating secant to the 4th of x, tangent of x dx. So again, it doesn't matter what power tangent is, power 1, power 2, power 10, it makes no difference. Here, this should be even though. And it is. It's power 4. So we're going to rewrite this as the integral of secant to the second of x. We're going to take off power. We're going to take off 2 from the power. So 4 minus 2 is 2. Tangent of x. And now here, secant squared of x dx will be our differential. Notice nothing's really changed. Put those together. That would be secant to the fourth of x, tangent of x dx. But now we're going to take this as our differential. So du will be secant squared of x dx. Okay, well if that's du, what does u have to be? What can you take the derivative of to get secant squared of x? That's the tangent of x. The derivative of the tangent of x is secant squared of x. So here we need all of the rest of this stuff to be in terms of tangent. Well, that's already in terms of tangent. And thinking back to trigonometry, how do I turn secants into tangents? Using the Pythagorean identity, of course. So here that's going to be the integral of, instead of secant squared of x, we can write that as 1 plus tangent squared of x. This expression here becomes this expression here by the Pythagorean identity. PYTH for Pythagorean. That's already in terms of tangent of x, so let me leave that alone. Secant squared of x dx. Oh, but now all of this is in terms of tangent, in other words, in terms of u, and that's your du. So this can now transform to the integral of 1 plus u squared, 1 plus tangent squared, 1 plus u squared, times u du. We can distribute that u to give us the integral of u plus u to the third du. And now, since that's polynomial, things are nice. Because now that's going to be the antiderivative of u, which is u to the second over 2, plus u to the third. Well, take the integral, that's u to the fourth over 4. And we have our antiderivative. So to find our we have an antiderivative. So to find our general antiderivative, we add our constant of integration, as the oracle foretold. So now, u is equal to the tangent of x, so we can substitute that back in, and our result in terms of the trigonometric functions that we started with, tangent squared of x over 2, plus tangent to the fourth of x over 4, plus some constant of integration. And that's our result. Okay? For our next example, instead of having a specific power on the secant, we're going to look for something that has a specific power on tangent. Let's look at a case where tangent has an odd power. We're not going to worry about what the power of secant is. Maybe it's even, maybe it's odd. Maybe there isn't even a secant at all. All we need is that the tangent should have an odd power. So something that looks like the integral of secant to the power m of x times tangent to the power 2k plus 1 of x dx. Again, m is any power we like, and that includes 0. It's possible you don't have any of those. And then here we have an odd power. Like that. Oh, actually, I take that back. I said it doesn't matter what power this is, even if it's 0. Actually, no. This should be any number except 0. Because if it is 0, we're left with only tangent of x, and that's tangent to a power of x, and that's going to be its own separate case. So here, this can be any power except for 0. Power 1, 2, 3, 4, 5. Just not 0. So here, this is any non-zero whole number. Oh, I guess I could say a non-zero whole number. I guess I could say any counting number, right? Any natural number. 1, 2, 3, 4, 5, and so forth. So if that's the case, we're going to strip off not just a single copy of the tangent of x, but also a single copy of the secant of x. So the way this will look is integral of secant to some power of x times tangent to an odd power of x. we're going to take secant to the power m minus 1. We took off a single copy of that. And then tangent to the 2k. Again, we took off a single copy of that one. And then that secant and that tangent that we took off, we're going to write down at the end secant of x tangent of x dx. And this will form our differential. Secant of x tangent of x dx. So let's take a look at an example of that. Example. Let's go ahead and integrate secant to the 5th of x tangent to the 5th of x dx. Like that. Okay, so we're going to take, well, first of all, notice that this is any power, as long as it's not 0. This is an odd power. That is what to look out for. Once this is any non-zero power and this is an odd power, that keys you to do the following. Take a single one of these, meaning you're left with just secant to the 4th power of x. A single one of these, meaning you're left with tangent to the 4th power of x. And now the two that you stripped off, one of each of these, come at the end. Secant of x, tangent of x dx. Okay, so we know we're going to use that as our differential. That's going to be our du. So if that's our differential, if that's our du, then u must be something whose derivative is secant of x dx. Oh, that's secant of x. The derivative of secant of x is secant of x tangent of x. So here, this is going to be our differential. This is going to be our du, which means everything else must be in terms of secant of x. Well, that's already in terms of secant of x. So we need to change this to be in terms of secant of x. Okay, so that's going to be the Pythagorean identity. I can change tangents into secants using the Pythagorean identity. Of course, the Pythagorean identity only works if this is an even power. So let me rewrite that ever so slightly. The integral of secant to the 4th of x times tangent squared of x, quantity squared, times secant of x, tangent of x dx. And now I can use the Pythagorean identity there. We can now write this as the integral of secant to the 4th of x times secant squared of x minus 1, quantity squared. Here, this tangent squared of x became secant squared of x minus 1. Since that's being squared, that's also being squared. Secant of x tangent of x dx. And now, everything is in terms of secant, except for this, which is my differential. So now, I can go ahead and rewrite everything in terms of my substitution. So it's going to be integral of u to the 4th times u squared plus 1. Oh, sorry, that should be a minus. U squared minus 1 squared. And then that expression is your differential du. This is nice, but can be made nicer if we distribute to give us a nice looking polynomial. We can write this as u to the 4th times u to the 4th minus 2u squared plus 1. Just went ahead and squared that. And then distribute that u to the 4th, and that'll give us the integral of u to the 8th minus 2u to the 6th plus u to the 4th du. And now that's polynomial in nature, which means this problem should be nice and simple. You just use the power rule. This will give us u to the 9th over 9 minus 2u to the 7th over 7 plus u to the 5th over 5 plus our constant of integration to make everything look pretty. And now we back substitute. Keep in mind that u is equal to the sine of x. So back substituting gives us our result in terms of our original trigonometric functions, and that's going to give us secant to the 9th of x over 9 minus 2 secant to the 7th of x over 7 plus secant to the 5th of x over 5 plus our constant of integration. So now let's take a look at a case where we have just a tangent or just a secant by itself. Note here we do need both of these because we need at least one secant and one tangent to make that work. In the previous example, we did not need tangent at all, but we did need secant to be an even power. So the remaining cases are, okay, what if secant is an odd power by itself? And what if tangent is just by itself, so I can't have both tangent and secant? So our next case is what happens when we have the integral of tangent to a power of, let's say, k x dx. So notice here, it doesn't matter what power that is. All that matters is that it's by itself. All right? No secants or any other function, just some power of tangent on its own. In that case, what we want to do is, instead of stripping off a single copy of this, we're going to take off two copies. So we're going to write this as the integral of the tangent of k minus 2 of x dx. So the power reduces by 2. And then over here, we're, not dx just yet, times tangent squared of x dx. And now using the Pythagorean identity, this would switch over to give us the integral tangent to the power k minus 2 of x times secant squared of x minus 1 dx. Once you have this, you can distribute and you'll have a new integral. This is a form of reduction formula. I've used that phrase before. You've heard me say that phrase before when we saw integration by parts. This is another category of integration which falls into the category of a reduction formula. Namely, you start off with the power of tangent, and now you reduce it to a lower power of tangent. Right? You're still integrating. You still haven't found what the result is, but you now have a smaller integral to work with. So, for example, incidentally, if this is tangent to the first power of x, you wouldn't do this because you already know the integral of the tangent of x, right? And if this were tangent squared of x, well then here it would just be starting from there. You'd have the integral of tangent squared of x, which you would convert to integral of secant squared of x minus 1, and you know how to do those. You know how to find the integral of secant squared of x and the integral of 1. So here, this really means it can be any power, but if it's power 0, that's boring because that's the integral of 1. Power 1, that's the integral of tangent, which you know how to do. And if it's power 2, tangent squared of x, you can write as secant squared of x minus 1, and you know how to integrate that. So really, this can be anything, but usually we mean for it to start at power 3 or higher. All right? So here, in fact, let's do that. Let's start with power 3. Tangent 3 of x dx. Okay, here it doesn't matter what the power is, even or odd. What matters is that it is tangent to a power on its own. No other trig function. Here we're going to rewrite this as the integral of, we're going to take 2 powers off of that. So 3 minus 2 is power 1. I can write tangent to the first of x, or I can just write tangent of x. And then I'm going to have the other tangent squared of x dx over here. Notice that's still tangent to the third of x dx. But now, by the Pythagorean identity, tangent squared of x is equivalent to secant squared of x minus 1. So we have this new expression. And now we can integrate. Well, these are 2 separate integrals though. So let's distribute first, and then we can integrate. So we're writing this as the integral of, let me distribute, that's tangent of x secant squared of x minus tangent of x dx. And here you can even split that up if you like. You can write that as two separate integrals. Tangent of x secant squared of x dx minus the integral of the tangent of x dx. But now both of these are integrals that we know how to do. Notice that we never actually got the answer from this formula. We simply got a new integral that we can hopefully now work with. Well, tangent of x, the derivative of the tangent of x is secant squared of x. So if you call this u, this right here is du. Tangent of x is u. The derivative of tangent x is secant squared of x. So this is u du. And the integral of u du is u to the second over 2. But since that's your u, that's just going to give you tangent to the second of x over 2. We'll have our constant at the end. That's your u. So this is u du. And the integral of u du is u squared over 2. Okay, so there's your u squared over 2. Minus the integral of tangent. That's something we saw in Cal 1. That's negative the natural log of the absolute value of the cosine of x. Yeah? If you don't remember how to do that, remember that's you can write that as sine of x over cosine of x, and then you can use the logarithm rule. After all, the derivative of the cosine of x is negative the sine of x. Here, double negative turns that into a plus, along with our constant of integration, as foretold by the ancients. So tangent squared of x over 2 plus the natural log of the absolute value of the cosine of x plus your constant of integration wraps up your answer. Okay, and finally the last case that we're going to look at. You'll notice that I'm really only looking at one example per case. It's because all of the cases would look pretty much the same. That's why it's a case. One case means one type of problem that works one type of way. So our last case that we're going to be looking at is, let's take a look at the integral of secant to the 2k plus 1 dx. We want secant to an odd power. Now, of x. Now, obviously, we don't want secant to the first power, even though 1 is an odd number, because we already know how to do that. Right? We saw that in Cal 1. We don't really need to worry about finding the integral of a secant function. That's what? Natural log of the absolute value of secant of x plus tangent of x. So here, really, we would start with power 3 and above. Okay, you say, well, why odd? What about evens? What happens if this is secant to an even power? Well, we already saw that. The very first case that we saw with secants and tangents had this being an even power, and it didn't even matter whether or not this was here. Notice, this didn't come into play except to be distributed in. If it wasn't there, well, there's nothing to distribute, but it doesn't take away from your differential. So if you have an even power of secant, we already know how to do that. That was our very first case involving secants and tangents. So the very last case that we worry about, the only one we haven't covered, is secant to an odd power. This one is slightly unexpected. Given what we've seen for all the other ones, you would think, okay, we're supposed to take off a copy of this and call it a differential, or 2 copies of this and call it a differential. Or we're supposed to use a Pythagorean identity and then form our differential. This one is the only one of its kind in this category, in this section. And this one uses integration by parts. So we're going to take a single example of this, and we're going to take, as I said, this is power 3 or above, so let's just start with power 3. Secant to the power 3 of x dx. Again, if that was power 5, 7, 9, it would work the same way, integration by parts. All right, so here we go. Let's take the integral of secant to the third of x dx, and we're going to write this in parts. Now you might say, well, I don't have parts. That's just one expression. Well, no. There's secant of x times secant of x times secant of x. So I really have 3 factors here, notwithstanding the differential. So what I'm going to do is I'm going to write it this way. I'm going to say secant of x, secant squared of x dx. Notice that this right here I could integrate on its own. If it didn't have that expression there, if it was just secant squared of x dx, the integral of that is just the tangent of x. So I know how to integrate this. Oh, well, if that's something I know how to integrate, that should probably be my dv, because I'm going to have to integrate that. So dv is going to be secant squared of x dx, which means v is the integral, which is just the tangent of x. Okay, well, if that's your dv, then this must be your u. Okay, so u is equal to the secant of x. So du must be secant of x tangent of x dx. Okay, so integration by parts tells me that this integral can be rewritten as u times v, secant of x times tangent of x, minus the integral of v times du. Well, secant of x tangent of x times another tangent of x, that's secant of x tangent squared of x. Dx. So now, this integral, you'll note that, well, tangent squared of x, that can be rewritten using a Pythagorean identity. After all, this is already a secant of x. Why not write this in terms of secant of x? We don't really have much of another choice, right? This doesn't fit any of the categories that we've seen previously, namely, we wish we had an even power of secant or an odd power of tangent. Here, that's the exact opposite. Okay, so we don't really have a choice to do it a different way, so let's rewrite it. After all, trigonometric functions can be rewritten lots of ways. So I'm going to write tangent squared of x using a Pythagorean identity. That's going to be secant of x, tangent of x, minus the integral of the secant of x times, instead of tangent squared of x, we can write that as secant squared of x minus 1 dx. So that becomes this. And notice that now we can distribute. We can say, okay, let's distribute the secant of x, and this will give us secant of x, tangent of x, minus secant of x times secant squared of x. Well, that's secant to the third of x. Secant of x times minus 1 is minus secant of x dx. Here, I can split this integral. I can write this as secant of x, tangent of x, and I can split this as this integral minus that integral. Now note that this negative applies to this entire expression here, so when I split this, I'm also going to distribute the negative. So let me write this one first, because it'll be negative, a negative, and that'll be a positive. So that's positive, the integral of secant of x dx, minus the integral of secant cubed of x dx, like that. All right, so minus a minus is plus, and then minus that integral secant cubed. Now this one I know. All right, this is one that we saw at the end of Cal 1. It's that strange one that involves the logarithm of a sum of trig functions. And that's secant of x tangent of x plus this right here becomes the natural log of the absolute value of the secant of x plus the tangent of x minus the integral of secant cubed of x dx. Notice that this is the same as this. In the end, your question is, how do you find the integral of secant to the third of x dx? Well, the answer is this minus the integral of secant to the third of x dx. That almost sounds like we went in a full circle. That sounds like we did something wrong, because how do I find this answer? Well, by knowing the answer. Well, that's the most circular logic ever, right? That's not going to get you an answer. Well, actually it does, if you consider what that means. I'm going to rewrite this expression, and I'm going to rewrite this expression as a single equation, skipping all the stuff in the middle. In other words, I'm just going to say this first line equals this last line. And by doing that, we'll get a nice answer. I'm going to write the integral of secant to the third of x dx is equal to the secant of x tangent of x plus the natural log of the absolute value of the secant of x plus the tangent of x minus the integral of secant to the third of x dx. Notice that these are like terms. You say, yeah, but I don't know what they are. I don't know what the integral of secant to the third of x dx is. It doesn't matter that we don't know what it is. We know they're like terms, which means we can combine. Let me add secant to the third of x dx to both sides of this equation. It doesn't matter that I don't know what that integral is to know that that expression plus another copy of that expression is double that expression. In other words, integral of secant to the third of x dx plus another integral of secant to the third of x dx, well, that's going to equal to 2 times the integral of secant to the third of x dx. So this plus this is double the integral that I was looking for. But now over here, these are gone. Number minus itself. Even though I don't know what these are, I know they're equal to each other. So if I have a positive one and I subtract away the other one, that's going to be 0. And these are left over. So I have 2 times my integral equals secant of x tangent of x plus the natural log of the absolute value of the secant of x plus the tangent of x. Here, that's 0. But now, notice that we're just about done. Because here, this is double our integral. Well, we don't want double our integral. We just want our integral. Okay, so divide both sides by 2. So here we get that the integral of secant to the third of x dx is equal to 1/2 times the secant of x tangent of x plus the natural log of the absolute value of the secant of x plus the tangent of x plus our constant of integration for that nice minty smell. And that's our result. So in summary, we've had 3 techniques for the sine and cosine functions. If you have an if you have an odd power of sine, strip off a single sine. If you have an odd power of cosine, strip off a single cosine. And if both powers are even, use your power reduction formulas. For secant and tangent, we've had 5 different techniques. If secant has an even power, strip off a pair of secants as your differential. If tangent has an odd power and you have any number of secants, strip off one of each and use that for your differential. If you have tangent to a power by itself, no secants at all, you strip off a pair of tangents there using the Pythagorean identity. This is a reduction formula. It doesn't quite give you the answer like the previous ones do, but it reduces your power to something that you can handle. And if you have an odd power of secant, then integration by parts is what you want to use. Now I said there's 5 techniques that we see for secants and tangents. That's only 4 if you counted those. So what's the last one? The last one is, if all else fails, no one said you had to leave them as secants and tangents. So case number 5, it doesn't really fall into any category in particular. It's just note if none of these techniques are valid for an integral of secants and tangents, or tangents, it may have one, the other, or both, your last-ditch effort is write everything in terms of sine and cosine. Just because we don't have a technique that's going to work for either of these functions doesn't mean that we won't have one that works for these. And that's the nice thing about trigonometry, that you're never really stuck. If the functions that you have in front of you are not encouraging, not useful, or not something that you know how to work with, you can always trade them in for other functions, namely sine and cosine. So as our last example, let's consider the integral of the secant of x over tangent squared of x dx. In this case, nothing really works because, well, we don't have any cases where we have tangent to a negative power. After all, that's in the denominator, that's a negative power. Well, maybe if we have secant to an even power, that won't matter. Well, sure, but we don't have secant to an even power, so it does matter. Okay, so here, if you carefully inspect the other 4 cases that we have, it doesn't fit into any of them. So as a final resort, we say, well, okay, secant and tangent are just not lending themselves to integration. We can always rewrite these things in terms of sine and cosine. After all, the secant of x is 1 over the cosine of x. Tangent of x is sine of x over cosine of x. But since that tangent is being squared, that means this expression is being squared. Here, that's going to be the same as saying the integral of 1 over the cosine of x. And now instead of dividing by a fraction, I will multiply by the reciprocal of that fraction. So that's cosine of x over sine of x, and then don't forget that's being squared. dx. Go ahead and finish that off. Go ahead and pause the video and go through this. And once you have your result, go ahead and unpause and we'll finish that one together. Alright, so here, that's going to equal to the integral of 1 over the cosine of x times, here that's being squared, so that's cosine of x times cosine of x, over, that's also being squared, sine of x times sine of x dx. And now cosine of x divides cosine of x, and we're left with a simpler expression of the integral of the cosine of x in the numerator, and our denominator will be sine squared of x dx. Note that the derivative of the sine of x is the cosine of x. So here, if I let u equal to the sine of x, that means du is the cosine of x dx, which is what my numerator currently looks like. So I can now write this as the integral of du over u squared. Or if we prefer, we can write that as the integral of u to the minus 2 du. In any event, we can integrate. Here, using the power rule, we can write this as u to the minus 1 over minus 1. Right, add 1 to that power, divide by the new power, plus that constant of integration. Of course, that u to the minus 1, we can write that in the denominator. So here we can even write as minus 1 over u. Right, negative brings it to the denominator, plus our constant. And then don't forget that u is a stand-in for the sine of x here. So that's going to be minus 1 over the sine of x plus a constant of integration. And here, 1 over sine of x can be written in an even simpler fashion, and that's to say the cosecant of x. So negative the cosecant of x plus that constant of integration that we love so much. And that is our result. Finally, don't forget that we have an entire course of trigonometric identities to take advantage of. If you run into a trigonometric expression within an integrand, you may need to simplify it, and it may have nothing to do with these cases. In some problems, you may simply have to rely on your knowledge of trigonometric identities and how to simplify those. Here, we're not going to cover all or even most of those because, of course, that is an entire semester of trigonometry, which, of course, everyone here has taken. So let's just, as a quick example, consider something that looks like this. Let's take the integral of the, let's say the sine of 2x times the cosine, let's make that sine also. Yeah, let's have the integral of the sine of 2x times the sine of x dx. Okay. Here, you might think, okay, well, that's a product, integration by parts. Maybe, but, well, let's see. I like substitution, but which one should I choose? Or maybe I should choose an argument. So here we have choices. And that's not to say any of those are necessarily wrong. But keep in mind that calculus is hard. Yeah, well, yeah, I know that. That's the whole point of the class, right? That's why there's lecture videos and study guides and all this other stuff that I need to go through. Well, yeah, but that's not what I mean. When I say calculus is hard, I mean compared to all the other math you've done. Well, again, now I'm just rubbing it in, right? Well, no, what I mean is calculus is hard compared to trigonometry. So why would I want to go through and do all of these tricks of calculus when trigonometry is something simpler to work with? If I can simplify or rewrite this using trigonometry, it'll probably be a lot simpler. Here, I have a double angle formula for the sine of 2x. So, instead of sine of 2x, I can write that as 2 sine of x cosine of x times that other sine of x dx. Notice that by writing it this way, now I have everything in terms of the same argument, which means now a substitution is a lot cleaner. It's a lot more likely to work. Notice sine of x times that sine of x, I can write that as the integral of 2 sine squared of x cosine of x dx. And now my substitution is just screaming at me. Right? If u is the sine of x, cosine of x dx is my differential. Note, I didn't have to go through any special cases, any integration by parts, or anything else that might come out a little messier. Calculus is hard compared to trigonometry and algebra. So if there's ever anything you can do to simplify using trigonometry or algebra, it's in your best interest to do it. It'll be faster, simpler, and a lot nicer in the end. So here, this is going to become the integral of 2 sine squared of x. We can write that as just u squared. Cosine of x dx, that's just du. And now the integral here is going to be 2u to the third over 3 plus a constant of integration. And since u is a stand-in for the sine of x, we can now write that in terms of our original trig function, sine of x. So we get 2 thirds sine cubed of x plus that constant of integration that we've all come to know and love. And that's our result. So keep that in mind whenever you have integration involving trig functions. Yes, we have these different cases for sine, cosine, secant, and tangent, and in some cases we may need to transform from secant and tangent to sine and cosine. But don't forget, you have an entire collection of trigonometric identities that you've known for, well, at this point, several years, right? Trigonometry, pre-cal, Cal 1, Cal 2. You've seen them for the last 2 years or so. Don't forget your double angle formulas, your half angle formulas, your power reduction formulas, your sum to product formulas, your product to sum formulas, and all those other ones that we've seen all through trigonometry and pre-cal and, well, ever since. So that is it for the section. If anybody has any questions, comments, or problems, please make a note of those and reach out to me. Let me know during office hours or during our next meeting. And I hope everyone has a nice day.